Manyere. I'm going to present a paper which was submitted to the ICCCS conference of the IEEE. The paper number is 122 and the title of the paper is Algorithm Performance Indexing through Parallelism. Image processing of spotlight synthetic aperture radar (SAR) involves large amount of data to be processed, and the time required to handle such data is relatively large. Evaluation of an algorithm in terms of processing speed and space is therefore a critical step in ascertaining suitability of an algorithm for a particular application. Major limitations in physical processing speed are principally associated with complex computations required to provide solutions to large size problems. With an increase in massive parallelism of processors, the overall processor operation speed has been seen to drastically improve, especially in image processing. The best choice of an algorithm on a particular processor and for a particular task is then based on the understanding of the performance of the algorithm and the hardware at hand. In this paper, we address this problem by providing a means to know the characteristics of a given algorithm by evaluating its performance. Two segmentation-based synthetic aperture radar algorithms, namely 1D and 2D, are evaluated and algorithm performance indexes drawn. What was the motivation of this research? The difference between processor speed and memory speed presents some tremendous performance challenges. In most cases, the processor has to idle or wait for the memory and other elements to accomplish their tasks for the next task to be performed. Some tedious computations, such as the fast Fourier transformations (FFTs), require some time to execute. In serial version, the FFT reuses the result of a certain computation. In parallel computing, the result cannot be reused since different processing elements generate results. Some computations have to be performed multiple times on a different processing elements at the expense of time. A detailed understanding of the performance of processors and algorithms of choice is particularly important where large data is to be handled. Hence, the need to index the performance of an algorithm in series or parallel processors, which is why this research was conducted. Now let's look at the synthetic aperture radar data, particularly the spotlight type. The SR data used in this research was simulated from the general expression of a motion compensated, sampled and stabilized received SR data. In general, the expression is given as S is equal to A subscript T summation from N equals to 0 to NP minus 1 summation of from K is equal to 0 to capital letter K minus 1, then e to the power j phi, which is also a function of n and k. Now phi is the phase of the data, which can also be expressed in terms of the sampling frequency, in terms of the center frequency of the chip, in terms of the range, okay, in terms of the pulse width, and so on and so forth. So this is the general expression for the phase of this is received as data. So RA is the slant range of the antenna phase sender to the scene sender. RT is the distance from the location of the antenna phase sender to the point target at time t. T subscript P is the pulse duration. R naught is the real-time range. TS is the sampling period. Fs is the sampling frequency. K is the sample number, and gamma is the chirp rate. C, the velocity of propagation of the electromagnetic wave, and AT is the radar cross-section area, often abbreviated RCS. Now, that such data is processed, it can be processed by these two new algorithms we're going to talk about, which is the 1D and the 2D algorithm. Now let's look at the 1D segmentation and the parallel formulation. The 1D segmentation algorithm segments data in either the first or the second dimension, each into multiple row or multiple column segments. Now these segments will contain some blocks of m over the number of processors, or n over the number of processors, where m is the number of samples on the row or the row dimension, and n is the column dimension. So we are saying that this data is segmented in first or second dimension. So the result are data segments which are then sent to the processors for processing. So the 1D segmentation algorithm segments data in first or second dimension, each into multi-row or multi-column segments containing a block of m over n np or n over np, consecutive rows or columns respectively, from an m by n size as data. In this case here, our np or npc represents the number of processors in the grid. The segments are then parallel processed into sub-images that are then recombined after processing to form a composite image. Now we look at the 1D data segmentation algorithm. This algorithm processes motion compensated as raw data. The raw data, which is in polar format, is reformatted using the 2D sync interpolation technique. After reformatting, we then check whether the data is exactly divisible by the number of processors. If not, the data is resized. Then the data is segmented into segments. And the segmentation can either be in the row dimension or in the column dimension. Then each segment is sent to a processor where it is then processed by range compression, then followed by azimuth compression. So the output of each processor is a sub-image. So these sub-images are then combined together to form a composite image. What about parallel formulation by 2D block segmentation? The choice of the shortest path to solve the problem is critical. Two methods of achieving the fastest path of solving a problem uses the vertices of data through source partition formulation or source parallel formulation. The source partition formulation partitions the vertices among n processors. Each processor computes the shortest path for all vertices assigned to it. On the contrary, source parallel formulation allows each vertex to a set of processors and applies the parallel formulation of a single source algorithm in order to solve the problem on each set of processors. The major limitation of source partition parallel formulation is that only n processors are kept busy doing useful work while the rest are idle. So this is the technique of parallel formulation by 2D block segmentation. Parallel formulation was therefore adopted in this research to improve the performance of source partition parallel formulation. Two-dimensional block segmentation was therefore implemented in this research, and this tool is useful for segmenting spotlight synthetic aperture radar data for parallel processing. Now, the second algorithm is the 2D segmentation algorithm, and this algorithm is different from the first one in that it segments the SR data in two dimensions. The first one, which was 1D, segmented the data in single dimension, either in the row or in the first dimension or in the second or column dimension. So we also process the motion compensated SR raw data, which comes in polar format, and the first step is to reformat it by use of 2D sync interpolation, and then we also check whether the data is divisible by the number of processors, which is the number of processors in the grid. If not, we also do 2D data resizing. Then the data after resizing is then segmented in the two dimensions, the first and second dimension. So we have got a block of data, a segment, which is then sent to a processor, and then it is processed by range compression, and then followed by azimuth compression. The result of each processor is the sub image, which is then sent to a mother processor where they are recombined to form sub images. The 2D segmentation is based on the segmentation of an M by N data in both first and second dimension. It should be noted at this point that when data comes, it is not always square. So it may have dimension M different from dimension N. So in this case here, we looked at data that came with the dimension M by N. So this data is segmented into segments, and the size of each segment is M over root of number of processors by N over root of number of processors. The processor, or each processor, which we may say P subscript ij processor, is then allotted a segment of the data, and then the processor keeps track of the upper left vertex or the corner of the lower, or the corner and the lower right corner of each segment. Now let's look at the performance parameters. A number of parameters can be used to analyze performance of parallel systems depending on the desired outcomes. Such parameters include execution time, the total parallel overhead function, the speedup, efficiency, and cost. Serial runtime is denoted by TS, and the parallel runtime by T subscript NP. Now, if the number of processors is N subscript PC and T naught is the total parallel overhead function, then the total parallel overhead function is given by T naught is equal to the number of processors times the parallel runtime minus the serial runtime. For any N by N data, the total parallel runtime would then be TNP is equal to 9TC N squared over NPC plus 2 brackets TS plus T subscript WN, where this becomes the expression for the total runtime. That is when we have TS denoting the serial runtime, TNP being the parallel runtime, and NPC is the number of processors. So for N by N data, this is the expression for the total parallel runtime. Now in that expression, our T subscript C is the time for each multiplying operation, TW the wait transfer time, and TS the start up time for data transfer. The value of the speed up, when we want to compute the value of the speed up, then that becomes S is equal to 90C n squared over T n P. That's the general value for the speed up for such a system. But when we consider the parallel time speed up, we can also express that as a function of problem size, meaning the size of the data or segment to be processed and the number of processing elements. So the parallel time speed up then becomes S is equal to n over npc plus 2 log npc, where n is the size of the data Now, ideally, the increase in speed up with increase in number of parallel processors is supposed to be linear. That is to say, when we increase the number of parallel processors, we expect the speed up to increase. So for a system with NPC processors, the speed up should be NPC. In other words, we are saying if one processor can take 1 second to process data, and we have got NPC processors, then when we use NPC processors to process the same data, we expect the processing time to be cut short by 1 over the number of processors. So in other words, we are saying the speed up should be equal to the number of processors. Now, due to some inefficiencies, speed up would normally be less than NPC in terms of problem size, and for a given number of processing elements, the efficiency is expressed as E is equal to 1 over 1 plus 2 NPC log of NPC over N, where NPC here is the number of processors in the grid. Now, the results that we obtained from this research, we start by looking at the performance index for 1D algorithm. Now, the number of parallel processors as well as the data segment sizes were varied, and then we determined the mean execution times for noisy and noise-free environment. Actually, we varied the number of processors from 2 to 32, and also the data sample or data segment sizes from 64 samples to 1024 samples. And then we used the 1D segmentation algorithm to process this data or these segments, and then we were able to evaluate the performance of the algorithm. So this is the the table that we got, or the results that we got. Right. For segment length of 1024, for segment length of 1024 samples, and using two parallel processors in noise-free environment, the runtime was evaluated, and we got 0.7635 seconds, meaning that this segment was processed in 0.7635 seconds. With the same number of processors and same size of the segment length in noisy environment, the processing time or execution time was 0.7903. We then reduced the segment length to 512 samples, increased the number of segments to 4, a number of processors to 4. For noise-free environment, processing time was 0.6351 seconds. And for the same data, in noisy environment, time was 0.6517. We then reduced again the sample size for the segment size to 256 samples, and increased the number of processors to 8. In noise-free, we had runtime or execution time of 0.5972, and in noisy environment, almost the same time, 0.5973. We then reduced further the segment length to 128 samples. Number of processors increased to 16, but we started to see a rise in execution time. So in noise-free environment, execution time was 0.6361, whereas in noisy environment, execution time was 0.6456. We further reduced the segment size to 64 samples, increased the number of processors to 32. In noise-free environment, the execution time was even higher with 0.73 seconds, whereas in noisy environment, execution time was 0.7334. So what are we saying? It can be observed that as the number of parallel processors is increased from 2 to 8, the algorithm performance improves, as seen from the execution time that decreased drastically. Diagrammatically, the result is as shown in the diagram, indicating that as we increase the number of parallel processors from 0 to 8, we see a drastic decrease in execution time with the minimum time at 8. Then when we increase the number of parallel processors, we begin to see a rise in execution time. Now, We then went ahead to compare the performance of this algorithm, which is the 1D algorithm, with the performance of the polar format algorithm under the same condition or under the same environment, noisy and noise-free environment. Under the same noisy or noise-free environment, the polar format algorithm took 3.085 seconds to process the segments of the data, contrary to 1D algorithm, which took 0.6 seconds. The 1D segmentation algorithm speed up time relative to the PFA was therefore about 5.142 seconds, or 5.142 times as fast as the PFA. Under the same conditions of noisy environment, the 1D algorithm cut the processing time from 3.683 seconds for PFA to 0.6 seconds, thus yielding a 6.138 times speed up. This is as shown in the table. So that's the performance of a 1D algorithm. Now we move to the performance indexing for 2D algorithm. The algorithm was evaluated in terms of its data processing speed for the noisy and noise-free environments. The number of parallel processors in the grid was varied, and the mean execution time recorded. The mean runtime showed a general decrease in execution time as the grid size increases to some point. The minimum mean execution time is obtained with 16 processors. A further increase in number of processors tend to reduce the efficiency of the parallel system. The performance index suggests that the algorithm has better performance in noise-free environment than in noisy environment, a general common trend for most algorithms. At best, the polar format algorithm took 3.085 seconds to process the SR data in noise-free environment, but the 2D algorithm took 1.0497 seconds with 16 processors to process the same data under the same environment, an effective 2.939 times speed up relative to PFA under the same noise-free environment. In noisy environment, the 2D algorithm was 3.344 times faster than the traditional PFA. Now, in terms of the graph or the index, this is the graph that was obtained when we indexed the 2D algorithm with the runtime on the vertical axis and the parallel processors on the horizontal axis. Now, in conclusion, in this paper, the 1D and 2D segmentation based algorithm performances were analyzed and indexed through parallelism. In both cases, the runtimes decreased drastically as the number of parallel processors were increased to a certain level, beyond which processing time began to rise irrespective of the number of processors added. The performance index suggests the algorithm's best performance in noise-free environment than in noisy environment, which is a general common trend for most algorithms. The results obtained validated the fact that systems do not run at twice as much when twice as many hardware resources were used. This is a result of some overheads associated with parallelism, which include inter-process interaction, idling, and excess computation. Now for the future scope. Improvement of time, of execution time, can be achieved by implementation of field programmable gate arrays FPGAs, which are faster than ordinary digital signal processors. However, FPGAs or FPGA implementation would require external storage memory or RAM to store the bulky received spotlight synthetic aperture radar phase history, the segmented data and output from the range and azimuth FFT, as well as output from the discrete cosine transformation in the 2D segmentation. These implementations are likely to improve both algorithms' performances to unprecedented levels.